Embedding Lemma and Tikhonov embedding. Definition: an indexed family of functions fi from x to yi where I element of capital I, where x and yi are topological spaces, is said to distinguish points from closed sets in X if for any small x element of capital X and any closed subset C of capital X not containing the point small x, there exists J element of capital I such that Fj of x does not belong to the closure of Fj of C in Yj. Here we can see that the point x and the closed set C are separated by means of a function Fj, and this concept is similar to that of complete regularity. This proposition proves the resemblance between the concept of complete regularity and that of distinguishing points from closed sets. The proposition states that a topological space is completely regular if and only if the family of all continuous real valued functions on it distinguishes points from closed sets. For the proof, let us assume that X is a topological space and family F is the family of all continuous real valued functions on X. Suppose first that X is completely regular. Consider a point small x element of capital X and a closed subset C of capital X not containing the point small x. Since the space is completely regular, there exists a continuous function f from x to unit interval such that f of x is equal to 0 and f of c is equal to singleton set 1 if c is non-empty. Then we can regard f as a function from x to set of real numbers also. So f is a continuous real valued function defined from x, and hence f will belong to family F, which is the family of all continuous real valued functions on x. And we can see that f of x, which is in fact equal to 0, and that it does not belong to the closure of f of c, since closure of f of c is equal to singleton set 1, since we know that all singleton sets are closed in R, as R is a T1 space. Therefore, closure of singleton set 1 will be equal to singleton set 1 itself. Thus, we have seen that there exists a particular member, namely small f, in the family F such that f of x does not belong to closure of f of c. Hence, we can conclude that family F distinguishes points from closed set. Thus, we have seen that whenever capital X is completely regular, the family of all continuous real valued functions on X distinguishes points from closed sets. Now, to prove the converse part, suppose that family F distinguishes points from closed sets, where family F denotes the family of all continuous real valued functions on the space X. Now, to prove that X is completely regular, take a point small x from the space capital X and a closed subset C of the space X not containing the point small x. Then, since we have assumed that the family F distinguishes points from closed sets, there will exist a map, say small f, from the space X to R, that is a function small f member of the family F, such that f of x does not belong to closure of f of c. Now we can observe that the singleton set containing the point f of x and the closure of f of c are two closed sets, since singleton set is closed in R, since R is a T1 space, and closure of a set is always closed, so closure of f of c is also closed, and f of x does not belong to closure of f of c. These two are mutually disjoint. So we can observe that these two are mutually disjoint closed subsets of R, where R is normal. By Urysohn's lemma, there exists a continuous function, say small g, from R to unit interval, such that g of first closed set, singleton set f of x, will be equal to singleton set 0, or we may write g of f of x is equal to 0, and the image of every point of this closed set f of c closure, the closure of f of c is mapped to 1. So we have g of f of x is equal to 0 and g of closure of f of c is equal to singleton set 1. Now let H be the composition of g and f. We know that f is a function from x to R and g is a function from R to unit interval. So this composition will be a function from x to unit interval, and clearly h of x will be equal to g composition f of x, and that will be equal to g of f of x, which is nothing but 0. Now let y element of C, where C is our closed subset of x, then h of y is equal to g composition f of y, and that is equal to g of f of y, where the point f of y is an element of f of c, and f of c is a subset of closure of f of c. So this is g of a point of closure of f of c, and we know that every point of closure of f of c is mapped to 1 by the function g. Hence, this is equal to 1. Thus, h is a continuous function from x to unit interval such that h maps the point small x to 0 and every point of c to 1. Therefore, the space is completely regular. So, we have proved that if the family of all continuous real valued functions on the space X distinguishes points from closed sets, then the topological space X is completely regular. Proposition: let family fi from x to yi, where I element of capital I be a family of functions which distinguishes points from closed sets in X. Then the corresponding evaluation function E from X to product yi is open when regarded as a function from X on to E of X. To prove that E is open, let us consider an open subset V of the space X. We have to show that its image E of V is an open subset of E of X, the subspace of product yi. That is, we need to show that E of V is a neighborhood of each of its points. For this, we need to consider an arbitrary point of E of V, and we need to show that E of V is a neighborhood of that point. A typical point of E of V is of the form E of X for some X element of V. Since X element of V, its complement X minus V will be a closed subset of capital X not containing the point small x. By the hypothesis, we know that family Fi is a family which distinguishes points from closed sets. There will be some member of the family Fi which distinguishes the point small x and the closed subset X minus V. By the hypothesis, there exists J element of I such that we have some function, say Fj, from the family of functions Fi's, such that Fj of X does not belong to the closure of Fj of our closed set X minus V. Now let G be the complement of Fj of X minus V, closure. Then, as closure of a set is closed and G is the complement of the closed set, G will be open in Yj. Since the projection function pi j, which is defined from product yi to yj, is continuous, and since G is an open subset of this codomain yj, the inverse image pi j inverse of G will be open in the product space product yi. Now we claim that pi j inverse of G intersection with E of X is a subset of E of V. If we can prove this claim, then as this quantity pi j inverse of G intersection with E of X is in fact an open subset of product yi intersection with the subspace E of X. So this intersection will be open in the subspace E of X using the definition of subspace topology. So if we prove the claim, then we are through. To prove this inclusion, let us consider a point from the set on the left side. Let y element of pi j inverse of G intersection with E of X. Then y belongs to pi j inverse of G and y belongs to E of X. Since y is a member of E of X, the image of X under the function E, we can express y as some E of small z, where z is a point of space X. Also, y element of pi j inverse of G implies that pi j of y belongs to G, which implies that pi j of E of z is an element of G. Since E is the evaluation function of the family Fi, E is the only function such that pi I composition E is equal to Fi for all I element of I. Hence, in particular, pi j composition E will be equal to Fj. So, we have proved that Fj of Z belongs to G. Then, Z must be a member of V. Otherwise, that is, if Z does not belong to V, Z will be element of X minus V, and hence Fj of Z will be a member of Fj of X minus V. And we know that Fj of X minus V is a subset of its closure, and from the definition of G, this is equal to Yj minus G. Thus, we have obtained that Fj of Z belongs to complement of G, which is a contradiction since we have already proved that Fj of Z belongs to G, not the complement of G. Therefore, the assumption that Z does not belong to V must be wrong. Therefore, Z must be a member of V itself, which will imply that Y, which is nothing but E of Z, must be a member of E of V. So, we have proved that an arbitrary element of pi j inverse of G intersection with E of X belongs to E of V. Therefore, we can conclude that pi j inverse of G intersection with E of X is a subset of E of V, as we have claimed earlier. Now we know that the set pi j inverse of G intersection with E of X is open in the relative topology or the subspace topology on the subspace E of X, and it clearly contains the point E of small x. Therefore, we have E of small x element of pi j inverse of G intersection with E of X, and that is contained in E of V, where this set is open in the subspace E of X. Therefore, we can conclude that E of V is a neighborhood of E of X. Since E of X was arbitrary, we can conclude that E of V is a neighborhood of each of its points, and hence E of V is open in the subspace E of X. Thus, E, when regarded as a function from X to E of X, is an open function. This completes our proof. Next is embedding lemma. It states that let Fi from X to Yi, where I element of capital I, be a family of continuous functions which distinguishes points and also distinguishes points from closed sets. Then the corresponding evaluation map is an embedding of capital X into the product space, product Yi. To prove this lemma, we need to assume that the family Fi is a family of continuous functions, and that it distinguishes points and also distinguishes points from closed sets. Then we need to prove that the corresponding evaluation function is an embedding of X into the product space product yi. We will obtain this theorem by putting together what we have already proved so far. For the proof, let us assume that E from X to product yi be the evaluation function. We already proved that the evaluation function of a family of functions, say fi where I element of capital I, is 1 to 1 if and only if the family distinguishes point. Since the family is given to be so, we can conclude that E is 1 to 1. Now, from another proposition, we also know that evaluation function is continuous if and only if each function in the family is continuous. Here we are given that the family fi is a family of continuous functions. Hence we can conclude that E is continuous. And from the last proposition, we know that E is an open map when regarded as a function from X to E of X. Thus, the function is 1 to 1, it is continuous, and it is open when regarded as a function from X to E of X. And we know that E when regarded as a function from X to E of X will be on to also. Thus, E when regarded as a function from X on to E of X is a homeomorphism. Therefore, E is an embedding from X to product yi. Next is a theorem which states that a topological space is a Tikhonov space if and only if it is embeddable into a cube. For the proof, let us first assume that the space X is embeddable into a cube. But we know that every cube is Tikhonov. Since Tikhonov property is hereditary, every subspace of cube will be Tikhonov. Since X is embeddable into a cube, X can be regarded as a subspace of the cube. Therefore, X must be completely regular. So we have proved that whenever X is embeddable into a cube, it is completely regular. Now we need to prove the converse. Conversely, suppose that X is Tikhonov. Let F be the family of all continuous functions from X to unit interval. Since the space X is completely regular, the family F distinguishes points from closed sets. Since the space X is T1 also, that is because a Tikhonov space is a space which is completely regular and T1. So our space X will be T1. So we have all singleton sets are closed. If X and Y are 2 points of space X, then X is a point of the space X and singleton set Y will be a closed subset of the space X not containing the point small x. Since family F distinguishes points from closed sets, there will exist some member, say Fj of the family F, such that Fj of X is equal to does not belong to Fj of singleton set Y closure. And this will imply that Fj of X is not equal to Fj of Y, since Fj of X does not belong to this closure. Therefore, family F distinguishes points as well. Therefore, by embedding lemma, the evaluation map E from X to the product of unit intervals is an embedding of capital X into the cube, and thus we have proved that whenever the space X is taken off, it is embeddable into a cube. The above theorem is the celebrated embedding theorem due to Tikhonov.